In this video we're going to look at the calculus of the trig inverse ratios. So as you can see there in the box, the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. And you can see that I've got that blast there that says, what do you notice? Hopefully you notice that the derivative of sine inverse doesn't involve a trig ratio. So nothing about trig here. So what does that then consequently mean when we come to integrate? It means you'll be integrating something with no sign of trig ratio in it, but you'll have to make the connection back to, in this case, sine inverse. I suppose a good thing about that is there's a format of the integral of sine inverse, so the integral of that fraction. It's got the a squared minus x squared in the denominator under the square root. So these are the features of that fraction that you have to recognise in a question if you're asked to take the integral of that. So this is purely a question where you are observing the seemingly minor detail of the question. The good thing about this is these questions will only appear in your Extension 1 exams. You will never get this question in an advanced exam. Extension 1 only. So yeah, you go into that exam or assessment task with that in mind, that you're looking for the integral of 1 over the square root and x squareds in the underneath the square root. So if a was 1, if it was just sine inverse of x, a being 1, then if you were looking to see how to differentiate it, you can see here how you would differentiate sine inverse of x. It would be 1 over the square root of 1 minus x squared. So it's, although the reference sheet doesn't show you the derivative, you can work out the derivative from the integral that's given on the reference sheet. Now, I'm going to go through the proof of the derivative being this, just because of the techniques that are used. Now, you know I frequently talk about that. Please note, the proof is not required to be learnt. So the reason I'm going through it is to show you this use and combination of unexpected concepts. You saw that in previous situations, and just the fact that we're making unusual connections is an awareness, is just an awareness tool for you to use later. There's no guarantee of the concepts you'll be connecting, but just be aware that there are times when, yes, you do have to just, it seems like you're plucking out of thin air these connections. The more you do, the better you'll get at that. So we're going to be using dy dx equals 1 over dx dy, or dy dx is, turn this one upside down, 1 over, turn it upside down. And you'll also be using sine squared plus cos squared equals 1. Now, I think that's a really, that is a common thing, the identity, sine squared plus cos squared is 1, but would it be one that you would necessarily have made a connection to in this proof? I'm not so sure, but yeah, just keep in mind that sometimes working through solutions requires you to make connections to things that you wouldn't normally connect to. Okay, so let's have a look. We're going to let y be the, if we're out to prove that the derivative of sine inverse x is this expression. So let y equal sine inverse of x, and ultimately we're looking for dy dx, because dy dx is the derivative of sine inverse of x. So using our definition of sine inverse, we could say that x is the sine of y. This comes from our understanding of sine inverse, there's a restriction on the y values. Now, the nice thing about this is we know how to differentiate sine of something. So we consider dx dy. That's all we can consider. Differentiate our x statement in terms of y, because we know that sine y would go to cos y. Now this is where, and you can probably see the connection. Dx dy becomes 1 over dy dx. This is the connection that's probably a little bit left field. Sine squared plus cos squared is 1, so we're going to take this cos y and write it as 1 minus sine squared y and the square root of all of that. The reason we're taking the positive square root only is for the restriction on cos of y. Continuing on, we know that sine of y was x from here, so sine squared y can be replaced with x squared, and cos of y is dx dy, so we can replace that cos of y with our dx dy. That comes from back here. 1 minus x squared. We don't want dx dy, so turn everything upside down or take the reciprocal of that, and we'll get our dy dx is 1 over the square root 1 minus x squared. Now, you've already seen the reference sheet, and it shows the reverse of this situation. Sine inverse of x on a is 1 over square root of a squared minus x squared. The reverse of that in terms of the integral of 1 over a squared minus x squared takes you back to sine inverse x on a. So could you please correct that? I'm not sure why that ended up going to this box when it should actually have gone to that box. This does not appear. This does not appear on the reference sheet. Now, it's up to you whether you learn this or whether you would come up with that by considering this as x times a to the minus 1. And yeah, that becomes a bit messy in there, but you can come up with this if you want to deduce that yourself, or on the other hand, you can learn this. Just learn this off by heart. So we've sort of got 3 formulas, I suppose, for the derivative of sine inverse. Sine inverse when there is a number other than a 1 in the denominator, and it becomes 1 over square root a squared minus x squared. The derivative when of sine inverse when there's just a single x, and so a is 1, is 1 over square root 1 minus x squared. And then when you've got the derivative of sine inverse of a number in front of the x, note you've got to have an a up here, square root 1 minus, and you've got to have an a squared there. Then just finally, what can be deduced about taking the integral of these things? The integral of 1 over square root of a squared minus x squared. Well, if we were taking the integral of this, we know it goes back to sine inverse x on a plus a constant. Or if you had the integral of a over square root 1 minus a squared x squared, it goes back to sine inverse ax. Why these are considered difficult? Why? Because again, there is no sign of trig inverse in this question, which is a little bit like when we were looking at our logs and differentiating log of x. It goes to 1 on x, and so the integral of 1 on x goes back to a log. No sign in the integral expression, the thing you're taking the integral of, that it's got anything to do with logs. However, you've got to know that. Same situation here. No sign that what you're taking the integral of has any connection to a trig ratio. So keep that in mind. Like I've said here in the notes, every question that you're doing or finding the derivative of, just realize that that is ultimately a possible future integration question. So really focus on these answers to the derivative of your sine inverse. And we'll do cos inverse and tan inverse as well. I'm going to stop the video there and do the, just work through the examples on the OneNote, and I may not even do a video on working through the examples, because if I show you every step, you will probably be able to follow that yourself without a video.